We recently finished talking about how to transform a random variable by shifting it or scaling it by some constant. But now we want to talk about how to combine multiple random variables together. It's a similar concept in the sense that we are applying a kind of transformation to the random variables by combining them. But instead of applying a simple shift or scale to one random variable, here we have two different random variables, and we're combining them together as either a sum or a difference. And this has all kinds of real-world applications. If we know how to do this, we can save ourselves some time, especially if we already have particular statistics about the individual random variables. So what we're saying here, let's go through an example as we do this so we can see what's actually going on. Let's say that we work for a company and we're trying to get an understanding of the total time that it takes for our company to get our employees paid. And we realize that what we really have here is two random variables. We have a set of data about how long it takes the manager of each department to approve the time cards or the timesheets of our employees. And then we have a separate set of data about how long it takes our payroll department to process those approved time cards or timesheets. But let's say that these two activities in total constitute all of the time that the company spends to actually get over the finish line of issuing paychecks to our employees. What we want to do is think about this set of data as the random variable x and this set of data as the random variable y. Of course, in this particular example, what we're interested in is a sum of these two totally separate random variables because we want to know the total time. If we add these together, the total time it takes our company to pay employees, which means we're going to be looking here, of course, at the sum of two random variables instead of the difference. Now, before we go forward with actually talking about the math of these calculations, the first thing we want to say is that it's important that our two variables be independent of one another. And the reason for that is because our standard deviation value, the standard deviation of the sum, is only going to make sense when we have independent variables. So these two data sets can't be affected by one another. But if we're confident that these two random variables, x and y, are independent of each other, then we can find their combination and calculate a mean, variance, and standard deviation for that combination. We also want to say that it's important that our two different random variables have matching units or units that make sense together. For example, if our first random variable is given in units of hours and our second random variable is given in units of square meters, so we have a measure of time and a measure of area, it doesn't really make sense to add those two things together or to find their difference. It's nonsensical to think about adding time to some area measurement. That's probably obvious, but we just want to make sure that our units are matching. So if our random variable x here is in hours, we want to make sure that our random variable y is also in hours so we can get total hours. And of course, if we were given two different data sets and maybe the first one is in terms of hours and the second one is in terms of minutes, we would want to convert the second data set from minutes to hours, or the first data set from hours to minutes so that we have matching units and it makes sense to add the two together or to find their difference. But assuming that we have independence and that our units are matching, let's go ahead now and talk about the idea of combining these two random variables. Before we do that, let's look at the data sets individually, starting with the mean of each data set. We're going to say for now that this is the entire population of data instead of a sample, which means that the mean is going to be given by the sum of these hourly values here. 1 plus 2 is 3, plus 2 is 5, plus 3 is 8. 8 divided by the number of data points, 4 is 2. So we have a mean of 8 over 4, or 2. And then over here, we'll say this is the mean with respect to the variable x. And then over here, the mean of the variable y here will be 2 plus 3 is 5, plus 5 is 10, plus 6 is 16. So we have 16 divided by 4, or 4. So what we're saying is that maybe our company has 4 departments in total, and the manager of the first department takes 1 hour to approve timesheets, the manager of the second department takes 2 hours, the manager of the third department takes 2 hours, and the manager of the fourth department takes 3 hours to approve timesheets. And then our payroll team takes 2 hours, 3 hours, 5 hours, and 6 hours to process payroll for departments 1, 2, 3, and 4, respectively. So we can say that on average, managers take 2 hours to approve timesheets, and on average, payroll takes 4 hours to process payroll for each department. So we have a mean for each random variable. And then, of course, we could also calculate variance. So our variance calculation, remember, we take each data point and subtract the mean. So here we start with this data point of 1. So we say 1 minus 2. We square that value, and then we add to that the same calculation for all of the other departments. So here we get 2 minus 2 quantity squared plus 2 minus 2 quantity squared plus 3 minus 2 quantity squared. And we divide this whole thing by the number of data points that we have, 4. And we'll divide by 4 because we're going to say that this data represents the entire population of our departments. If this was a sample of a larger number of departments in our company, we would divide by n minus 1, or in this case, 4 minus 1 or 3. So we'd be dividing by 3 instead of by 4. But since we're going to say that this represents population data, we'll divide by n, the total number of departments here. So the result then is 1/4. 1 minus 2 is -1. Quantity squared is a +1. So we have 1 here. This will be 0, 0, and then 3 minus 2 is 1. Quantity squared is 1. So we get 2 divided by 4, or 1/2. So our variance then is 1/2, and then standard deviation is the square root of that, or 1 over square root 2. If we do a variance and standard deviation calculation for the variable y, we start with each data point, subtract the mean. So we get 2 minus 4 quantity squared plus 3 minus 4 quantity squared plus 5 minus 4 squared, and then finally the last data point, 6 minus 4 quantity squared. And then again, we're doing a population calculation, assuming that this is the entire population. So we divide by the number of data points, which is 4, or multiply that by 1/4. And if we simplify here, we get 1/4, and then we'll get 2 minus 4 is -2, quantity squared is +4. 3 minus 4 is -1, quantity squared is 1. 5 minus 4 is 1, squared is 1. And 6 minus 4 is 2, squared is 4. And so we get 4 plus 1 plus 1 plus 4 is 10. 10 divided by 4 is 5/2, or 2.5. So we can say then that the variance of y is 5/2, which means that the standard deviation of y is the square root of that, or the square root of 5/2, the square root of 2.5. Now, here's where the idea of combining random variables really comes in handy. Let's say that we've already been collecting this data about the amount of time that our managers spend approving timesheets and the amount of time that our payroll team spends processing payroll for each department. So assuming we already have all of this information, if we now want to calculate the sum or difference of these two data sets, we don't have to start over from this raw data and create a whole new data set for the sum or the difference, and then go through the process again of calculating mean, variance, and standard deviation for the new data set. If we already have these summary statistics, then we can go directly to these formulas and use them to find the sum or difference of the two variables. So for instance, we can see here that the mean of the sum is equal to the sum of the means. In other words, to find the mean of the sum, we simply add the two means together, 2 plus 4, and we get 6 hours, which means that total payroll processing time between the managers and the payroll department, if we add up all that data together, our mean is 6 hours per department. And similarly, if we wanted to find the difference, the mean of the difference, we would simply take the difference of the means. So we could take 4 minus 2 to get 2. And we could say that on average, the payroll department spends 2 hours extra per department than the managers spend per department on the process of getting the employees paid. Realize here that there are a few different ways that we can prove this to ourselves, one of which being that we can actually create a new data set. We'll call it the sum data set. And we find the new data set for the sum by adding data points from these original data sets X and Y. So if we take 1 plus 2, we get the new data point 3 in the data set for the sum. If we take 2 plus 3, we get 5, 2 plus 5, we get 7, and 3 plus 6, we get 9. This is now a new data set where we've summed the data points in sets X and Y. And what we realize here is that if we take the mean of this new data set, we would add 3 to 5 to get 8, plus 7 is 15, plus 9 is 24. We get 24 divided by the number of data points in the population, 4. 24 divided by 4 is 6. And we see that we get back to this value we already found. Same thing here, if we create a new data set for the difference, we'll say a new data set for the difference. If we take 2 minus 1, we get 1. 3 minus 2, we get 1. 5 minus 2, we get 3. And 6 minus 3, we get 3. Now we have a new data set for the difference. And if we take the mean here, we get 1 plus 1 is 2, plus 3 is 5, plus 3 is 8. 8 divided by 4 is 2. And we get back to the mean for the difference that we already found. Now, in the same way, if we want to make a variance calculation for the sum or the difference of X and Y, we don't have to build this new data set for the sum and then start fresh with a variance calculation for this new data set. We don't have to find the data set for the difference and then start fresh with a variance calculation for this data set for the difference. Instead, we can use the fact that we already have variance values for both X and Y and use these formulas here to calculate variance. So the variance for the sum is equal to the sum of the variances. So we take 1/2 plus 5/2 is 6/2 or 3. So we get a variance of 3. And then similarly here for the variance of the difference, to find the variance for the difference, we take the sum of the variances. So again, we get 3. Now, while we're here, it's important to mention what we just said here. The variance formula that we used to find the variance for the sum and the variance for the difference was identical. When we find the variance for the sum, we add the variances. And you would think that when we find the variance for the difference, we take the difference of the variances, like we did up here with the formulas for the mean. But instead, we find the sum of the variances again. And that's because both data sets bring their own variances to the table. And even when we combine them into a new data set for the sum or a new data set for the difference, we're not eliminating any of the spread of the data set when we do that. And so the variance for the new data set, whether we're finding the sum or the difference as our combination, the variance is still going to be found by summing the two variances from the original data sets X and Y, which means then, of course, that our standard deviations for both the sum and difference are also going to be the same. The standard deviations will be, of course, the square root of the variance. So the standard deviation of the sum will be square root 3 hours, and the standard deviation of the difference will be square root 3 hours. Keep in mind also that it's invalid for us to find the standard deviation of the sum or difference directly. In other words, notice here in our table of formulas that we are combining the means and the variances, but we don't have formulas for the standard deviation. And that's because we can't find the standard deviation of the sum by summing the standard deviations. And we can't find the standard deviation of the difference by summing the standard deviations or taking the difference of the standard deviations. The only way to get to standard deviation for the combination is to first find the variance of the combination by summing the variances of the original data sets, and then to take the square root of variance in order to get standard deviation. So the whole takeaway here is that if we find ourselves in a scenario where we already have summary statistics like these ones, we've been maybe tracking this information across two data sets, X and Y. So in this case, we've been keeping track of how many hours it takes managers to approve timesheets for each department. And we've been keeping track of how many hours it takes our payroll team to process payroll for each department, such that we already have a mean, variance, and standard deviation value for both of these independent random variables, X and Y. then when we want to find the sum or difference of these two variables, when we want to find the combination, what we realize is that we do not have to start from the beginning and combine these two data sets into a new data set for the sum or a new data set for the difference and start completely from scratch with a mean, variance, and standard deviation calculation for this new data set or this new data set. Instead, if we already have this information, we can go straight to these formulas and immediately and directly make these calculations here to see the mean, variance, and standard deviation of both the sum of these random variables and the difference of these random variables, which just means that we want to keep in mind that when we already have this information, we can move quickly to the combination and save ourselves a lot of time redoing the math from scratch with a new combined data set. And of course, that can be really helpful when we're trying to answer real-world questions like the one we were here, where we were trying to get a total for the complete number of hours spent across our entire company, collecting all departments together in order to get payroll processed from beginning to end, or the difference between these two departments on the amount of time spent on payroll.